Hi, my name is Dr. English, and today we're going to continue our conversation about chemical formulas. Specifically, we're going to be looking at the basics of writing binary ionic compounds. So the first thing that we're going to look at is redefine what is an element, talk about what is a compound, look at empirical formulas, have a tiny review of ionic bonding, looking at binary ionic compounds finally, writing ionic compounds, the rules that we have to follow, and finally summing it up with a little shortcut method called the Crisscross method. So the first thing that we need to do is talk about elements versus compounds. So what is an element? Elements are composed of only one type of atom. So only a single type of atom makes up an element. Elements cannot be broken down into a simpler substance using chemical methods. So in our world in chemistry, the simplest form of an element is an atom. So if we we have some different examples down here. We have titanium or oxygen, bismuth, which I always think is fascinating looking, sulfur, and finally gallium. These are all examples of one type of atom that make up an element. Now let's talk about what is a compound. A compound is defined as a substance composed of two or more different, and that is important, different elements that are chemically combined in a fixed proportion. Now, what do we mean by fixed proportion? So if we look at this formula right here, H2O, remember there is a assumed subscript of 1 right there. So that means that the ratio here is 2 hydrogens for every 1 oxygen. And to make water, to make H2O, we always need to stick to that proportion. A 2-to-1 proportion of hydrogen to oxygen. That's what they mean by fixed proportion. If you deviate from that at all, you don't have water anymore. A compound is also defined as a substance with constant composition. So that means the same throughout, that there's no variation whatsoever. A substance with constant composition that can be broken down into elements by chemical processes like burning. So in a compound, which is not just a single element, but a compound can actually be broken down into its individual elements that it's composed of. So in this case, if we look at the example of water, water can be broken down to hydrogen gas and oxygen gas through a process called electrolysis, which we'll talk about later on in the year. Now let's talk about the concept of an empirical formula. An empirical formula is going to show up a lot in the next couple of units, and we introduce it here because a lot of our binary ionic compounds are already in the form of an empirical formula, so it's good to know what that means. So an empirical formula is defined as a formula of a compound that expresses the smallest whole number ratio of atoms present. So empirical formulas can exist for either ionic or covalent compounds. And we haven't talked about how to name covalent compounds yet, but we're going to get to that. So if we look at this example right here, aluminum oxide has the formula Al2O3. That means that the aluminum to oxygen is in a ratio of 2 to 3. And there's no whole number that can divide into 2 and 3 and make it smaller. So basically, aluminum oxide represents an empirical formula because the subscripts here are in the lowest whole number ratio. Now let's look at caffeine. Caffeine is C8H10N4O2. What divides into all of those numbers equally? If you said 2, you're correct. So I can take each one of these subscripts and divide it by 2, 2, 2, and 2, and say the empirical formula for caffeine is C4H5N2O. And we really don't need to put the 1 there because the 1 is basically assumed. So this would be considered the empirical formula of caffeine. The real formula for caffeine is C8H10N4O2. If I wanted to build caffeine, that's what I would need to make that particular molecule. But the smallest whole number ratio of the elements would be this one that we see right here. Let's review what an ionic bond is one more time. So ionic bond is obviously made up of ions, and it is the full transfer of electrons to form positive and negative ions. Typically, ionic bonds are going to occur between metals, which are going to give up electrons, and nonmetals, which are going to accept them, and they're held together by electrostatic forces, that positive-negative force of attraction. So if I look at this little animation over here, I have two atoms, and I'm going to say that this is my metal and that this is my nonmetal over here. So when they form an ionic bond, the metal over here is going to lose its one electron, the atomic radius is going to get smaller, and it's going to get a positive charge because it's lost electrons. On the same point, the nonmetal gains the electron, the radius gets larger because it's gaining that electron, and it has an overall negative charge. So we see a full transfer of electrons from the metal to the nonmetal, and then we have a positive negative force of attraction holding those two ions together, which is known as an electrostatic force. Now let's talk about binary ionic compounds. And if you look at the word binary, the prefix bi right here means two, and then ionic means ion, and then a compound. So basically what we see here is two different types of ions coming together to form a compound. So an ionic compound, which contains the ions of only two elements, typically a metal and a nonmetal. That's not always the case, but typically that's what we're going to see in this course. So here's an example. Sodium chloride, NaCl, will contain the ions sodium and the chloride ion. So Na plus 1, it's lost its valence electron. Chlorine minus 1, it's gained a valence electron to get its full octet. Another example is magnesium oxide, or MgO, which contains magnesium ions and oxygen ions. These are all considered binary ionic compounds because they have one metal and one nonmetal. But if we look at these, we'd say that all of these are in a 1-to-1 ratio, losing one valence electron here, accepting one valence electron here, losing two valence electrons here, accepting two electrons. One thing that you have to realize is that in ionic compounds, we might not be in a 1-to-1 ratio. For example, CaF2, calcium fluoride, is in a 1-to-2 ratio, one calcium for every two fluorine ions. Or Al2S3, we need two aluminum ions and three sulfide ions, and that's what these subscripts are basically representing. Or then finally, lithium oxide, two lithium ions for every one oxygen ion to form these ionic compounds. How do you write ionic formulas? Well, general rules. Atoms with positive oxidation numbers will be written before those with negative oxidation numbers. Typically, this is going to translate into your metal being written first and your nonmetal being written second. Now remember, the algebraic sum of the oxidation numbers must be equal to 0. In other words, electrically neutral, and we just talked about this when we assigned oxidation numbers in the last video. So for an example, a sodium ion combines with a fluoride ion, and the result is a neutral compound whose formula is NaF because the +1 and the -1 cancel each other out. Or a calcium forms a positive 2 ion, and fluorine forms an ion with a -1 charge. Therefore, you need two fluorine ions to balance out the one calcium ion, and the resulting formula is CaF2. So calcium gives up its two valence electrons. Each fluorine atom has 7 valence electrons. Each can gain 1 electron. So therefore, I need two fluorine atoms, each to gain an electron to get two fluorine ions. That is why we are in a 1-to-2 ratio. So a lot of times when you write out these formulas, you can look at your metal and your nonmetal, and you can say to yourself, what's losing electrons, what's gaining electrons, how many do I need of each, and those will actually match up to your subscripts. That's one approach to writing these ionic formulas. The other way of doing it is the one that I like, which is known as the Crisscross method. So this is a shortcut technique for writing formulas for ionic compounds. And some of it is just basic, what we've already looked at. Some of it is a little bit more involved. So let's look at our first example here. Na plus 1, F minus 1. I have a +1 and a -1. Now they're going to cancel each other out. So when I write these, this is just NaF. And they're in a 1-to-1 ratio. So these could have subscripts of 1s down here, but we don't need to put those in because those are assumed. So NaF. Let's look at another example. Mg plus 2 and F minus 1. So what we're going to do here, because the superscripts are different, what we're going to do is we're going to basically cross them down. So I'm going to take this +2 and I'm going to make it a subscript over by the fluorine, and I'm going to take this -1, and I'm going to put it down by the magnesium. Now, there's a rule here, and the rule is no positives, no negatives, no ones. You could say that to yourself over and over again. No positive charges, no negative charges, no ones. So when you cross these down, don't bring the positive sign, don't bring the negative sign, and don't include ones. So when I rewrite this, this will be MgF2. MgF2. The 2 comes down, but not the plus sign. The 1 is assumed, the negative sign is not brought down. So the correct formula for Mg plus 2 and F minus 1 is MgF2. Let's look at another one. Ca plus 2, O minus 2. The plus 2 and the minus 2 are going to cancel each other out, so it's just CaO in a 1-to-1 ratio. Then we look at this one, Cu plus 2, P minus 3. Again, we're going to cross these down. So the 2 is going to go down here, the 3 is going to go down here. But remember, no positives, no negatives, no ones. So this is going to be Cu3, P2. And these superscripts now definitively become subscripts. When we write chemical formulas, there are no superscripted numbers unless you have some type of polyatomic and it has an overall charge. So if you look at these, no positive signs, no negative signs, no ones. So what did we go over in this tutorial? We reviewed what an element was. We talked about the definition of a compound. We introduced ourselves to the concept of an empirical formula. We did a tiny review of ionic bonding. We looked at the rules for writing ionic compounds. We introduced the concept of binary ionic compounds. And then we looked at the crisscross method. Need more help? Feel free to contact me. Have a great day.